This video is going to cover tributary loading for two-way systems. So for a two-way system, our equation is just slightly different from a one-way. This time L2 over L1 is less than or equal to 2. So this means it's a very square-ish shape. So not long skinny hallways, but very, very square-ish looking things. So again, L2 is the longer distance of the rectangle or square. L1 is the shorter distance of the rectangular square. And we are very specifically talking about the one rectangle that happens to be in here. So each of those rectangles is a different rectangle. So we're talking the L2 to L1 ratio for that particular rectangle. And that will be a two-way slab. And just to draw out what's going to happen with this, we're going to go at a 45-degree angle in from the corner. So if you think about it, you're in like a rectangle and you want to know what's the closest wall. Well, if you're here, the closest wall is obviously this wall. If you're here, the closest wall is obviously that wall, and so on and so forth. But when you're at that 45 degree, you kind of have a choice. Maybe if you're over here, the wall is down. And if you're in the dead center, you're like, well, which way do I go? Well, obviously you're not going to run all the way over to L1. You're probably either going to go up or down. So the shape that we're actually looking for here is a trapezoid. So we're thinking geometry, and we need to remember 45 degrees. So the angle of this line here is 45 degrees. And that's for every single one of those. So every single one of those lines is at 45 degrees in from that corner. So you come in 45, which, just doing a little bit of math, 45 here to make this triangle shape means that this is going to be half of L1 and half of L1. And then where it hits the 45, remember the special thing about 45 is that the length and height of a triangle is the same. So this is also half of L1. And this is also half of L1. So the remainder of whatever it is for the base of this part right here, that remainder is just going to be L2 minus L1. So we have a trapezoid shape for the L2 direction, and we have triangle shapes in the L1 direction. Let's see how it all plays out in an example. So here in this example, we have a kind of very small slab here. We have a 4 meter wide and 3 meter tall for each of the bays for A, B, C, and D, E, F. We're going to assume that A and F and C, D over here do not act on A, B, C, nor does it act on D, E, F. So we're just going to assume that those guys there are not actually acting on those long girders. Our slab is made of 270 millimeter thick stone concrete, and we want to draw the loading diagram for all members. So step number one, we need to find out what type of slab that we have, if it's one way or two way. So our L2 is 4 meters and our L1 is 3 meters. And 4/3 is 1.33, which is definitely less than 2. So this is a two-way slab. Again, it's very closer to square shaped, right? 4 is not that much greater than 3, so it is kind of square-ish shaped. Next, we probably want to draw out that shape. So at our 45 degrees, as best as we can here, kind of just draw out our shape. This is totally to scale. So we've got our triangles and our trapezoids here. Remember that that is going to be acting at 1.5 meters for where that central piece is. So if that's at 1.5, we've got 1.5, 1.5. That's total of 3, which means this middle piece totally to scale is only 1. So 1 plus 1.5 plus 1.5 is 4. So that is the geometry of our loading diagram. Next, we kind of need to know what is the weight of the slab. So we need to go to table 1.3, and at table 1.3, we find that 0.023 kilonewtons per meter squared per millimeter of depth is the weight of stone concrete. So our dead load is equal to the 270 millimeters of depth times 0.023, again, kilonewtons per meter squared per millimeter. Our millimeters cancel, and we're going to be left with 6.21 kilonewtons per meter squared. So our dead load is acting across the entirety of A, B, C, D, E, F, that whole giant rectangular thing. Our dead load is acting across that rectangle. And our shapes here are showing us which direction our loads are going to go. So again, we're going to take that shape and we're going to go to the nearest member. So the nearest member, it could be up. The nearest member for this triangle is going to be out, going horizontally, and the nearest member would be going down or out the other way. So we need to find all of those directions for all of those shapes. Again, this is kind of like a fire escape. You know, you're just trying to see where's my nearest exit and get to it. So the closer you are to that wall, and that wall is your fire escape, obviously that's the one you're going to pick. So that's our loading diagram for our member, or for all of our members there. So next we need to actually draw out for our individual members what we have going on. So we'll start with AF. AF is an end member, so AF is going to look the exact same, funny enough. AF and CD, they're going to look the exact same. And we're looking for which arrows are pointing to that member. So that's going to be this shape right here. We've got this shape of a trapezoid there, which again, it's the same on the other side. It's the absolute same shape on the other side. Just so happens because all of the dimensions are the same. So if we're trying to find how much dead load we have on our thing, first off, we need to draw that shape. And that shape we said is a trapezoid. So there's our trapezoid, probably still horribly drawn. But, you know, it is going to be 1.5, 1, and 1.5 meters. We want to know what's the height. What is that total height of that trapezoid? So what is W? So remember, we have this dead load, the 6.21 kilonewtons per meter squared acting over the whole thing, and AF is across 4 meters. So we're not looking at the 4 meter direction, we're looking at the vertical direction. So what is the vertical height of this? That is 1.5. And again, same on the other side. So our W here is equal to the dead load times 1.5 meters. So that's going to give us 9.32 kilonewtons per meter. So this is our loading diagram for AF, and do remember that is the exact same for CD. Doesn't actually change in the slightest for those. Now if we go look at our middle member, BE, what does he look like? Well, it's again, he's the same type of shape, right? We do have the trapezoid, but we do happen to have two trapezoids. Look at that. Would you look at that? Two trapezoids here, one on each side. They are not going in opposite directions to cancel out. They're merely showing that all of the dead load that's on this side is going to act on that member. So it's actually the same shape. It's the same trapezoid. So we're drawing the same trapezoidal shape, which is again totally not to scale, but good enough. So again, 1.5 meters, 1.5 meters, and then one in the middle. It is the same shape. All loads going down on it. And the height of this, the weight that's going to be applied to that is going to be a little bit different because we are looking for the height of it, which is again the 1.5, but there's two 1.5s, right? There's a 1.5 on each side. So we're going to have our dead load, W being equal to our dead load, times 1.5 plus 1.5 because there are two of the same trapezoid adding together there. So he's going to equal double our last guy, which is going to be 18.6 kilonewtons per meter. And now if we want to go and find the loading diagram for our long member, that's A, B, C, and D, E, F. Remember that in our problem statement we said that A, F, and C, D do not act on A, B, C, and D, E, F. But that does mean that B, E is going to act on those members. So because of that, we need to find the reactions here. So you can solve this in two ways. The technical way that we're doing is we're going to say sum the moments about B and you'll find the reaction at E, right? You can do that. Because this is an absolutely symmetric shape, I do know that half of this is going to apply to one of my reactions and the other half is going to go to the other side. Again, this is only the case because this is a purely symmetric shape. And if you don't trust it, maybe don't like this math style, you can always sum the moments and find out the truth. But we're going to be left with, I'm going to start with the triangle. The triangle is 1/2. That base of the triangle, 1.5. The height of the triangle is W. That's the triangle here. Right, I've got that guy. Then I need half of that rectangle. So the rectangle is the base of 1 times the height of W, but it's actually, right, that's the whole rectangle. But I only want 1/2 of the rectangle, so I need to multiply by 1/2. So my reaction force that I'm going to find is 23.3 kilonewtons. So he's going to act at B and at E. So he's literally acting at B and at E on either side, right? If this is A, B, C, or D, E, F, it's acting at that same spot. So this is 23.3 kilonewtons. Next, we need to go see what's our loading diagram. What does it actually look like? Well, remember that we do have these triangles. These triangles are acting on our member there. So that's our shape. Our shape is going to be those triangles. Very lovely triangles I've drawn here. And we want to know what W is on these triangles. So again, remember that we have the total width here of A, B, C, and D, E, F. We know that this is 3 meters and this is 3 meters. So we're not looking at the 3 meter direction. We want to know what is the height. What is the height? What is this height right here? That's 1.5. So our W is going to be equal to the dead load times 1.5. That's the total height of that triangle. So that W again is 9.32 kilonewtons per meter. And if you want to find what the reaction forces would be in the columns, if say there was a column at AF and if there was a column at CD, you could easily find those reaction forces, but that is the loading diagrams for those members for this two-way slab.